Hey, we have here today another integral on the board. We have the integral from 0 to pi over 2 square root of tan x dx. And I know I've done something really similar to this. I can't remember if I did it as an indefinite integral or if I had different bounds, but I thought I'd still do this problem, but just kind of do it a different way. So to start with, what I'm going to do is actually break up my tangent into sine over cosine. So I'll just rewrite this and we'll split up the radical. So I'll write it as sine x, square root of sine x over the square root of cosine x. But then of course I can rewrite these radicals and I can write this as sine to the 1 over 2x times, and I can write this cosine as cosine to the minus 1 over 2x dx. But now that we have our integral in this form, we can just notice the similarity of this to the beta function. Okay, so we have our formula here for the beta function, and we just noticed that we've got our sine and cosine function, we got the right bounds. We have this 2 out front that we can deal with later. So we just need to figure out what this z1 and z2 value is, and then we can get into our solution in terms of the gamma function. So first we're saying the exponent on the sine is in the form 2z1 minus 1, and we have our exponent here of 1/2. Well, then with this we can just solve for z1, and we find z1 is going to be 3 over 4. Then doing the same thing for cosine, we see that that exponent needs to be in the form 2z2 minus 1, and that value is going to be minus 1/2. But then just solving for z2, we find that this value is going to be 1 over 4. So now that we have z1 and z2, we have everything we need for this formula over here on the right. Now because we don't have the 2 on the integral, I can just use this formula and divide by 1/2 in order to get a form for something that's just like our integral. So we'll bring a 1/2 in front here. We'll have gamma of our z1, which is 3 over 4, and then gamma of our z2 is going to be 1 over 4. And then the denominator, we just have gamma of the sum of these two, the sum of z1 plus z2, but that's just 1. Okay, so from here we just need to calculate this thing and see if we can get some simplification in order to finish this off. So we do have this formula to convert the gamma function into factorial. It's just gamma of n is going to be n minus 1 factorial. So for our gamma of 1 in the denominator, gamma of 1 is just the same thing using this as 0 factorial. But 0 factorial is just 1, so I'm going to cross that off. Now to calculate the gamma of 3/4 or the gamma of 1/4 is actually more complicated, but what we can do for this is use Euler's reflection formula. Okay, so we have Euler's reflection formula over here on the right, and we notice this isn't exactly the right form. Like either one of these values can be our z, but let's just say our z is 3/4. Well, 1 minus 3/4 gives us 1/4. So what I'm going to do for this formula is I'm just going to take, it's going to work out the same either way, but I'm going to take my z to be 3 over 4. And then so what I can do for these two values, we can write gamma of 3/4 times gamma of 1/4. Using this formula, we're just going to have pi over sine our z value, which is 3/4 pi. But then 3/4 pi we can write as 1 over square root of 2, and then I can just take that and bring it into the numerator. So we can write this as square root of 2 pi. So just plugging this back in over here, we can finish it off. So for our final solution, we're going to have square root of 2 times pi all over 2 from the 1/2. And that's it. Okay, pretty interesting problem. We'll stop it there. Thanks everyone for watching. Have a great day.